In this video, we look at the 2015 higher level physics question on particle physics. This year it was question 10a, so it was a full question worth 56 marks. So there's some text in the exam paper questions, which I'll read out. So there are about 1 trillion neutrinos from the sun passing through your hand every second. Neutrinos are fundamental particles and are members of the lepton family. Leptons are not subject to the strong nuclear force. So that's the background. Then what they ask us is, what is the principal force that neutrinos experience? So the principal force that neutrinos experience is the weak nuclear force. They experience the other three forces, but the weak nuclear force is the one that impacts them the most. The second section in this asks us, electrons are also members of the lepton family. Name two other leptons. So again, I've been a bit exhaustive here in terms of notes. We have electrons, which wouldn't count. So electron neutrinos, muons, tauons, ordinary neutrinos, or any of the antiparticles, any of those would be fully correct for full marks. Then it says name one fundamental particle that is subject to the strong nuclear force. So quarks and antiquarks are fundamental particles that are subject to the strong nuclear force. The strong nuclear force binds the nucleus together, whereas the weak nuclear force is responsible for holding the atom together. So it makes sense that the electron, which is outside of the nucleus, wouldn't experience the strong force like protons in the nucleus do, but the weak nuclear force that would bind the atom together will be responsible for keeping the electrons in place. So the next thing I have here is just a little bit more theory on quarks, because it's not something I've gone over in my videos to date. So the quarks have 6 different flavors. So that's the word that they use. So it's flavors of quarks. So they're up and down, strange and charmed, top and bottom. You also have the anti-up, anti-down, anti-strange, anti-charmed, anti-top, and anti-bottom, and then the symbols for it. So that bar, that line over the top, is used to denote an antiparticle. So we have our up and our down with our anti-up and our anti-down. So they're the quarks. The next chunk of this question deals with Pauli. So it says Pauli proposed that a neutrino is emitted during beta-decay. Why did he make this proposal? So the answer, Pauli proposed a neutrino as this was needed to ensure the conservation of mass energy and momentum. So without accounting for the neutrino, mass energy was not conserved and momentum was not conserved, so the neutrino was needed to explain this. They ask us then to write a nuclear equation to represent beta-decay. They tell us that during beta-decay, a neutron decays with the emission of a proton, an electron, and a neutrino. So that makes it a little bit easier. So this is our neutron over here. So that decays, so that's the radioactive process. That gives us this here, which is denoted as the proton. Often use H for a proton, but you could use P. This gives us our electron, 0 mass, or effectively 0 mass, and a charge of -1, and then our neutrino. So we check charge +1 -1, 0, mass 1, 0, which gives us 1, and the neutrino then would have a charge of 0 and a mass of 0. So that is our basic formula for beta-decay. So then the next thing we're asked to do is we're asked to calculate the energy released in mega electron volts during beta-decay. So again, this is a typical question that you'll have. You need to find the energy released in mega electron volts. So that energy in this case comes from the loss in mass. So we go to our tables and we find the mass of the neutron, we find the mass of the proton, and we find the mass of the electron. They're all listed in there. With loss in mass, the neutron is a reactant, so that decays, which gives us a proton and an electron. So this, I'm not counting the neutrino because that is effectively 0 mass, even compared to the electron. So this works out to be our decrease in mass. I rounded it off here. Again, maybe you don't have to, maybe I shouldn't actually, in fact, but I did here. We're not going to make too much effect on the answer anyway when we round it off into mega electron volts, but I would typically just deal with all the numbers. So that's 3,946,3174, and that I rounded that off to 1.395 by 10 to the minus 30 kilograms. So that's the loss in mass. We then use Einstein's equation E equals mc squared. I took the speed of light from the tables, again 2.99792,458 by 10 to the 8 meters per second. Again, include your units to keep things on track. So we take the loss in mass multiplied by the speed of light squared, and this is our energy in joules. So 2.53 by 10 to the minus 13 joules, and again I rounded that off, which I probably shouldn't have there. I probably thought it was finished. But we then need to convert this into electron volts, so I take my number of joules and multiply it by this figure here, which again can come from our tables, which gives us this many electron volts, which we then round off to 2 decimal places for 0.78 mega electron volts. So that is the energy from this reaction, the energy released. Next, it says an electron can be detected in a cloud chamber. However, it's more difficult to detect a neutrino, so explain why. So, a little bit of background. A cloud chamber is a chamber where moving charged particles produce tracks that can be seen. That's how they found the electrons. So the charged particles, negative charge, produces tracks that can be seen. Your positron, the first antiparticle discovered, that was also seen there, that would move in a different way to the electron. A neutrino, on the other hand, has no charge, so it cannot be detected as easily in a cloud chamber. It cannot be detected in a cloud chamber because it's charged particles. A neutrino only interacts weakly with matter, so that's the second reason. So it barely interacts with matter and it has no charge, so there are your two reasons. Next we get into a bit of mathematics. So it says in a cloud chamber, an electron travels perpendicular to the direction of a magnetic field of flux density 90 millitesla, and it follows a circular path. Calculate the radius of the circle when the electron has a speed of 1.45 by 10 to the 8 meters per second. So I start off, as I usually do, by taking down my quantities and getting their numbers. So magnetic flux density is one of our first numbers, which is given at 90 millitesla. So I convert that into SI units of 90 by 10 to the minus 3 Tesla. We're told it's in a circular path, which is again important information, so I'll pull that out. I'm asked for the radius, and I'm given the velocity of the electron, which is 1.45 by 10 to the 8 meters per second. Seeing that it's traveling in a circular path, it's going to experience a centripetal force. Centripetal force is mass by velocity squared over the radius. It's also in a magnetic field, so there's going to be force due to the magnetic field, and that is given by QVB. Again, V being the velocity. So charge, velocity, and this B is our magnetic flux density. So I can equate these two things from Einstein's equation. Every force is an equal and opposite reaction. Force equals force. So my centripetal force is going to be equal to the force due to the magnetic field. So B is again your magnetic flux density. So I let the two forces be equal, so that gives mv squared over r equal to qvb. First, I look at my symbol. So m is mass, v is velocity in both cases. R is the radius, Q is the charge, and B is the magnetic flux density. Seeing that we're dealing with the same thing, we have an electron traveling at a particular speed. Both B's and both M's are going to be the same. First thing I do in my calculations is I want to get this in terms of R. So the first thing I do is I make it linear, so I multiply both sides by R, which gives me this line here, mb squared equals RQVB. I then divide across by these three terms, so I get R is equal to mb squared over QVB. My velocities, the one on the bottom, cancel with the squared. So then what I get is mv over qb. I sub in my values from the question at this stage, including my units. So I get this equation here, and that gives me a radius of 9.16 by 10 to the minus 3 meters. So that is my radius, so it's quite a small radius. If you're looking for more in your textbooks, you can go from page 301 up to 308. That deals with a lot of this magnetic field stuff. The last thing I'm asked in the question is, describe the path of a neutrino in the same magnetic field. So that question was dealing with an electron in the magnetic field. So a neutrino only interacts weakly. It will have no deviation in a magnetic field. It has no charge, so it will not interact in a magnetic field, and it only has a very small mass, and it does not interact weakly with matter. So the neutrino, long story short, will travel straight in that magnetic field. So that is the end of that question. Again, a bit different and a few different things thrown in. That circular motion I haven't seen in any other year, but again, the course does overlap, so they can link things together however they see fit. But if you know these workings, you know these calculations, you know what to do, all they can really change is the numbers. The ideas will stay the same.